Hai and salam sejahtera. My name is Nitya Arisa, anak perempuan Wirat. My number matric is CD210313. I will present the introduction and the calculation for this project. The uphill roller is a beautiful physics demonstration first reported by English mathematician William Laban in 1694. In the original version, a double cone placed on two divergent inclined ramps appeared to roll uphill, apparently violating the laws of physics. The familiar double cone demonstration is illustrated in Figure 1 below. This demonstration is known as the cone rolling uphill. It consists of a double-sided cone that has pegs on either side where the center of mass of this cone is in line with those pegs. Along with this cone, we also have a V-shaped track that we elevate on one side. The idea of these demonstrations is to illustrate how the center of mass of an object will determine how it will roll up or down and help.
My name is Putrina Shafika binti Razaidin, matrix number CD210018.
Technical or theoretical description. Double cone roll uphill. The uphill roller is an example of the center of mass of an object descending under the influence of gravity. Over the past 3 centuries, this demonstration has remained essentially the same. It has been incorporated into arts and science museums as hybrid. It is also utilized in many, if not most, introductory physics courses. By replacing the double cone with the sphere, something really counterintuitive can occur. Depending on the angles of inclination and divergence of the ramps, the sphere can ascend or oscillate back and forth, reaching an equilibrium position near the center of the ramp. Uphill rolling condition. The condition for the double cone to roll uphill is tan theta less than tan alpha tan beta. You can see it on this figure. The figure 1. The inclined line represents the top surface of the rails. The bottom end of the slope, shown at the left-hand side of figure 1, is at a distance from the ground. The top end of the slope on the right-hand side of figure 1 is at a distance b from the ground. The figure also shows the cross-section of the double cone after it has rolled somewhere up the slope. The point in the middle of this cross-section is the double cone center of gravity, which we call G. The angle of the inclination of the roller is imposing a coordinate system on this plane as shown. We give the point G the coordinates x and y. As the double cone rolls up the rails in center of gravity G, move along a path given by some equation y equal to fx. Our aim is to find this equation. At the figure 1. For the figure 2, view from the front. From the point where the two rails meet, we see the cone as if it had been sliced vertically and lengthwise. Again, we see the center of gravity G as well as the points P and Q where the top surface of the two rails meet the double cone. The point G1, P1 and Q1 are the projection of these 3 points of the ground. The angle gamma is half of the angle at the apex of the cone. For the figure 3, the diamond shape is the shadow the double cone casts on the floor, and the two lines emanating from the point P1 and Q1 are the shadows cast by the two rays. Aiming at the point O and at the angle 2 beta, as before, the points G1, P1 and Q1 are the projection of G, P and Q. With the coordinate system from figure 1 in place, we can find the equation of the path of the center of gravity of the double cone as it rolls up the slope. For convenience, we write SY for the straight line, the segment running from a point X to a point Y. Figure 3, the calculation. Okay, now let's take the front view from figure 2. Write S from the point that lies on the line from G to G1 at the same height as P, and write R for the apex of the cone which lies on the line from G to G1. At the figure 4, there is some calculation and some formula. For the figure 5, you can refer that it has a same view like a figure 1, and there is also some formula for calculation on that.
For the calculation, we need to design the double cone that can roll uphill with length 20 cm. To begin with, we will place our column on the lower end of the track, which is also the skinny end of the bit, and this item will end up resting on the track at a very low point on the object if we place our cone at the skinny end of the track. So now we know the position of our center of mass. So from the demonstration, it looks as though the column actually travel uphill as it travel along our track. If however we check the center of mass of this object on our indicator, that the center of mass is short from the surface. So how possible that this went uphill? Well, we know that this is a V-rail track, therefore when the object is on the lower end, the track is only separated by a small amount, but as it travels along the track, the length of the track gets separated more and more. Therefore, as the cone travels up the track, the separation of the track touches a higher and higher point on the cone. Thus more taking the whole object and dropping it lower on the track. Thus more the difference of height from the bottom end of track to the top end of track, and the different height from where the center of mass starts on the lower end to the track to where it ends on the higher end of the track differs. So on top, it looks like the comma traveling uphill. The center of mass of the object was actually traveling down.
Hi, my name is Tuan Nur Azlan Amira Bukituan Nizan and my metric number is CD210309. I am presenting about result and discussion. Viewed from the side, a rolling double cone appears to defy gravity and roll uphill. Upon inspection, it is seen that because the ramp widens, the CG of the double cone actually drops and is, in fact, rolling downhill. Let us have a closer look at the triangle track. It consists of two rails, PQ and RS. The distance between P and R is less than the distance between Q and S. Thus, rails PQ and RS are not parallel to each other. The ends PR are at a height h0 from the ground level and the ends QS are at a greater height h0 plus h above the ground level. This is a two diagram that shown top view and side view. Next, this diagram shown about the center of mass G of the double cone lies at a point where the axis of symmetry intersect the plane of symmetry. Let R be the radius of the cone's circular base. When the cone is at the lower end, PR, its center of mass G is at a height Hi equal to h0 plus R above the ground. The center of mass of the one starts coming down as it moves from the lower end to the upper end. At the upper end, center of mass G is at the height Hi equal to h0 plus h. The track and double cone are made in such a way that R equal to h. Thus, the initial height Hi is greater than the final height Hf. Next, let's talk about other which are relevant. The double cone is a very important quadratic surface. It for no other reason than the fact that it's used to define the so-called conates, ellipse, hyperbolas, and parabolas, and all of which can be created as the intersection of plane and a double cone. This topic attached with link for double integrals, which is from script. Application of double integrals, calculating the moment of inertia of a lamina. Moment of inertia or second moment can be defined as a measure of tendency of matter to resist a change in rotational motion. This is the formula about moment of inertia about y-axis, x-axis, and z-axis. Also, I'll attach with formula about application of triple integrals and multiple integrals. Application of triple integrals. Apart from finding the volume of a solid, similarly to the double integrals, the triple integrals can be applied to find the mass, moment, center of gravity or centroid, and moment inertia for solid. That's all from us. Thank you.